Bismillahirrahmanirrahim. Assalamu alaikum. It's me Atif Fakas, and today in this lecture of BS Physics Elementary Mechanics, I am going to explain the conservative forces and non-conservative forces. Dear students, in our previous lecture we discussed that potential energy is associated to a system, to a conservative system, because of its configuration. And now we are going to discuss the forces that are conservative forces, the forces that are generated by the conservative systems, how can we distinguish a conservative force from a non-conservative force. Today we are going to explain all these things. Let me define the conservative force. You can state it as if the work done by a force is independent of the path, the force is conservative. What does this statement mean? It means that let's suppose we are having a system, we are having a conservative system, and in that system I am taking 2 points, one is point A, the other is point B, and the system then is such that there is a conservative force in that system, and that conservative force performs work. And if the work done is such that by choosing any path of these two, path 1 or path 2, if the work done is same, then the force that is doing that work is conservative force. And there is another definition of the same conservative force. We can also define it in terms of work like this. The total work done by a conservative force in a closed path is 0. And that can be explained this way. If the conservative force performs some work on taking an object from point A to point B, first it takes from here to here, and then it takes from B to A. And if the total work done, if I add all those works and I get 0 as a result, then I can say that the force involved there is a conservative force. And in case of the motion from A to B, the work done can be explained by this integration. It is integration from A to B, and using path 1, and F dot dr is that infinitesimal amount of work. And for that small work, force is parallel to that displacement dr, and this is the infinitesimal amount of work, and this is an exact differential for a conservative force, which we are going to discuss. And if work done is same for both the cases, then the force is conservative. And then if we want to prove it using this definition, then we can do like this. If we add these two works, they would simply be doubled. But if we subtract these two, why would we subtract these two? If I take work done from A to B, I would get this. And then if I change the integration signs, then I would get negative sign here. And then if I add them, I would get 0. So in either case, if we check the work done is total work done is 0, then the force is conservative, and the work done is independent of path, then the force is conservative. And then there is a mathematical condition for checking whether a force is conservative or not. And for that, the first thing is that you should be having that small infinitesimal amount of work such that it is an exact differential. And we are going to discuss that condition for checking a function to be an exact differential soon. It must satisfy a test, and that test is such that let's suppose I consider some two-dimensional case, and then this differential that is F dot dr, that can be expressed this way using calculus. So fx dx plus fy dy, and in order for this to be an exact differential, this must satisfy this condition dfx with respect to y and dfy with respect to x should have same results. And if any force satisfies this condition, we can say that the force is conservative. And then we can check some forces we know about whether they are conservative or not. For example, you can take example of a gravitational force and you just check it. I write here the gravitational force in components form and you just check it whether it is a conservative or not by applying this test. And if I express the gravitational force mathematically, Fg is g times some mass m, some other mass m, divided by r square. Here I would write some unit vector r. This is the gravitational force. And now I say that I need the components of this gravitational force. Then I would represent this in vector form. And if I write vector here, unit vector is a vector divided by its magnitude. And here I was having r square. So I would get g times m divided by r cube times some vector r. This is the gravitational force. Now if I represent this x is the vector sum of x, y and z components of a position vector, then I can write f sub g equals g m divided by r. I would be having x I plus y j plus z k. So you expressed it in terms of x, y, z. Now just check this way, separate this into the components. How can you do that? This is magnitude of the total vector and it is associated to every component of that vector. And if the force is a three-dimensional vector, so it would be having three components. In one I would write xi. This one is its x component, and now this would be its y component. If I write this way, and that would be its z component. So this is how I resolved that vector into its components. And now if I want to check whether the gravitational force is conservative or not, I can apply this test. If I differentiate this one with respect to y, I would be getting something, and if I differentiate it with respect to x, I would be getting something. And if I check the two, if the two are same, the force is conservative, otherwise it is a non-conservative. But you just check it, it would satisfy this condition. And then we can look at the conservative forces from another perspective. We can come from the conservative fields, and if you just take some potential energy and you take its negative gradient, you get a conservative force. And how can we do that? Let's suppose we are having some conservative systems which we discussed in our previous lecture, where I told you that when work is done against any conservative system, that work is stored in it in the form of its potential energy. And if some infinitesimal amount of work stores some infinitesimal amount of energy into that object, into that system, then we can write this, and we already know about this negative sign because the work is against that field. So this is that amount of potential energy, infinitesimal amount of potential energy that is stored in that conservative system. And here this work is done by some conservative force. So if I write this way, minus F dot some very small amount of that infinitesimal displacement. So it is F dot dr, and that is equal to du. And that F is such that it is parallel to that small infinitesimal amount of displacement. So I can ignore that vector signs, and I can simply have minus F dr, and that is equal to du. And from here you can see that F can be represented as the negative differential with respect to r of that. And I can also write this in vector form is force is minus gradient u. This is the negative gradient of potential energy. Gradient, you know about gradient. It is the differential operator, and in 3 dimensions we define it this way. It is it's a differential operator. And now if you apply this operator to some potential, and this time I am having absolute gravitational potential energy of myself. I am standing here at the surface of earth, and there is some potential energy involved, my absolute potential energy, and that is gm, mass of earth, my mass, and distance between me and the center of earth. So this is my absolute potential energy here at this point. And now if I take a negative gradient of this function, here r is x square plus y square plus z square. And now if I take negative gradient of this function, I would get force, and that force would be my weight. That force is a conservative force, that force is a gravitational force. And let's see whether we get that force. Okay, so F equals what? Del u, and curly or curly x I plus curly or curly y y j plus curly or curly z k unit vector applied to this voltage v, potential u. And now if I substitute this value here in this expression, and I apply all these differential operators one by one, what I get: curly or curly x that U, which is G M divided by this R, that is x square plus y square plus z square 1 by 2 with unit vector I. And then curly divided by curly y. Once again this function, this time having unit vector j. And then this is plus curly or curly z, the same function, unit vector k. And if we solve these differentials one by one, first let me differentiate this function with respect to x, what I get. First of all, I take this part, and the same is here, gm divided by this all x square plus y square plus z square raised to the power 1 by 2, and the same with this one, x square plus y square plus z square 1 by 2. So I am first taking this one, and let's see what we get. Divided by x square plus y square plus z square raised to the power 1 by 2 with some unit vector I. And this way, if I take the constant g, m and m outside, g, m, I get this function 1 divided by some function raised to the power 1 by 2. So if I change a bit before applying the differentiation, let me change this denominator to numerator by changing the sign of its power to minus 1 by 2, and then it's very simple. So differentiation, just differentiate it, the power becomes the coefficient power rule, x square plus y square plus z square raised to the power minus 1 by 2 minus 1. And if you differentiate this function once again with respect to x without the power, you get 2x with some unit vector I. And then if you simplify this, you get minus g m, and then this function x square plus y square plus z square raised to the power minus 3 by 2 with that x I. And if I replace this x square plus y square plus z square by this r square, because if you take square on both sides, you get r square equals to this, and then I substitute it here. R square minus 3 by 2, 2 cancels with 2, xi, and then I get minus gm divided by r cube. This minus 3 becomes r cube and multiplied with xi. This is now the x component of that force which I derived from some scalar potential energy, and this is a conservative force. this is x component of gravitational force. And then for this part, if we repeat the same procedure, if we differentiate this function with respect to y, then I would get gmm by r cube, but here we would be having yj unit vector. And then if we differentiate the same function with respect to z, and we take k unit vector with it, we get the z component of that conservative force, gravitational force, and here we would be then having z with the unit vector k. So concluding that discussion, let me write all those components which I would get from here. From first I get this. F is, from first what I get, minus G M divided by R cube xi. This comes from first term. And then from second term, minus gmm divided by r cube with yj. And no equality sign here, and here minus the third gmm divided by r cube z with unit vector k. And this way, here you see I am having some negative sign. So why this negative sign comes here? That is because I ignored to put negative sign here while I was applying the gradient. While I was taking the gradient of potential energy, I should have put a negative sign here, and that would then appear here, and then that would make this whole equation multiplied with -1, and here we would be getting plus sign. So I get this force by just taking all these things common, because they are common, and what I get, xi plus yj plus zk. And then if I replace this xi plus yj plus zk by some vector r, so it is the gravitational force, and so I proved it to be conservative. I have derived this from my absolute potential energy, and this is my absolute potential energy here at this point, and this is my weight. If you are not familiar with this expression of gravitational force, then you can substitute this vector by what? By gmm, can the magnitude multiplied with some unit vector and divided by r cube. But this r is then cancelled with this square cube, and here we get r square, and from here then we have some unit vector r. So it is the gravitational force. The small m is my mass, capital M is the mass of earth, g and r is the distance between me and the center of earth, and I can calculate my weight from here. So this is how we can show that the gravitational force is a conservative force. So to derive a conservative force from some potential is very easy. You just take negative gradient of potential energy and you get the force. We can take another example of mass attached to spring, and I hope with that you would understand this concept completely. You just take another potential energy, and that potential energy is this time the energy stored in an object that is attached to some spring, and that potential energy of this object, when it is stretched to this point, its potential energy becomes half kx square, and we know that already. So if I differentiate this function with respect to x and I take negative gradient of this function, so what I would get the force, and I would get a conservative force. And how? That is negative gradient of that potential energy. So minus curly or curly xi plus curly or curly yj plus curly or curly z k of that u. And you know that here we are having only one coordinate x, and it's one dimensional case, so I would get only this part, that is half kx square with some unit vector I, and the rest are 0. Y independent, z independent. It's the function that has no y, no z. And here I'm having minus kx with some unit vector I. So I get force, and so this is yet another example of a conservative force. So this way we can check whether force is conservative or not. To check the force to be conservative, we apply that condition which I did earlier. But now when you have some potential energy, so obviously potential energy is only in the conservative system, then you can get the conservative force by just taking negative gradient of that potential energy. So it's enough for today. Inshallah we'll meet in next lecture with some new concepts. Take care. Allah Hafiz.